This is video 7 for Computer Science 3344, and we're going through the machines like crazy now, aren't we? We did the NDFA for a long time, and then we did push-down automata for a little while, and now we're all ready for a new one. The good news is this is the last one. I'll review the relationships that we already know. We know that regular languages have that love and feeling for finite automata, NDFAs, and deterministic finite automata, all those good things, the finite automata in general. Those are the ones that look at an input symbol, go to another state, look at another input symbol, and so forth. The one-way trip. And we sliced and diced those every which way but loose with grammars and also regular expressions and so forth. But those match up. A regular language, you can construct a finite automata and vice versa. If you got a finite automata, you can reverse engineer the regular language. We also looked at context-free languages. Those have got their own thing going with push-down automata. And you can write it out if you want. In the interest of time, I'll abbreviate. PDA, push-down automata. Push-down automata was like a finite automata, and the stack is included so that we can actually remember stuff. And context-free refers to of course, the format of the production rules. Regular was very restrictive. These are a little less restrictive, and then at the top of the heap are the unrestricted languages. That was the grammar where anything goes. Anything could be replaced with anything in a production rule there. No business of, well, it's got to be a single terminal symbol followed by a non-terminal or whatever. We don't have anything like that. Just anything as long as there is at least one non-terminal on the left-hand side. And that is so much unrestricted that it's almost like no restriction at all. Who do they get along with intimately? Well, it turns out that this being the wide open space that it is, it's got a wide open space kind of machine to go with it, the Turing machine. What do we have to do to beef up what we already know so that we get up to the level of a Turing machine? Well, a finite automata, to make that recognize more complicated languages, we had to add a stack. So you might think, oh, something big has got to happen here. Actually, it's not all that big. It almost is going to look like a push-down automata, except we're not restricted to only looking at the top of the stack. That was a restriction on a push-down automata. We could use that as a memory, but we could only see and replace what was on top of the stack. The Turing machine is going to relax that and let us just zip around all over what's called the tape. It's a string of symbols that we've recorded. We can look anywhere we want, front, back, middle, top, bottom, whatever. So that's the only restriction we need, relaxation we need to make it all the way up to the top of the line, the Turing machine. And I don't know if I can get a Turing machine to find up here or not, but I'll see if I can. This is a working definition. A Turing machine, which we'll add to our toolbox of abstract machines that do things with languages. Abbreviated TM is a 7-tuple, bunch of pieces. And that's why I'm not sure I can get all this on the board. But I'm going to give it a shot. I'll see if I can do 2 columns, and that way I don't have to erase and write everything all over again. Well, let me get the 7-tuple up here. It's capital M, and it's the 7-tuple that has these pieces. Capital Q, capital sigma. Ah, yes, we recognize those. We've seen those before. Those are in our other machines. Capital gamma, we've even seen that in our push-down automata. Little delta. And who else we got here? Q0. Ah, yes, all of our favorite actors back for more with our grand finale curtain call. Q0, Q accept, that's a newbie, and that's a QB. And Q reject. Okay, I'll spoil the surprise. Q accept is what we used to call a final state. It's an accepting state. If we go there, then job done. Whatever the Turing machine was trying to do was successful. It could be recognize a string since it can do all the things that these two other machines can do. Q reject, we saw that in roughly an incarnation with our trap states that we had for finite automata. If you go to Q reject, you're done. You can't get out. It's machine hell. You go there, there's no way you can pull yourself back out, unfortunately. So that's all the pieces, but I need to make it official since this is the big one. Q, I'll abbreviate. We know Q. Q's a set of states. What state the machine is in. Capital sigma, we know that as well. That is our input alphabet. Now, I'm going to do another step here after I get capital gamma up here. Capital gamma, instead of calling that the stack alphabet, since it's not strictly a stack, even though we could use it as a stack if we want to, it's called the tape alphabet. We can still only store symbols in a straight line, just the way a stack stores them in a straight line, a linear container. The tape is a linear container as well. In other words, it doesn't have a two-dimensional array unless we go to an awful lot of trouble. But the tape alphabet is the symbols that could show up on the tape, and that's what I want to double back here. Capital sigma, make that as a note. Capital sigma, not an element of, no, is a subset of capital gamma. In other words, anything that could show up at the input is a valid tape alphabetic symbol. So it's like the tape alphabet has all of our input symbols in it, and then some additional stuff. So again, I keep mapping it back to things we know. Why am I doing that? The push-down automata, when we were remembering zeros and ones, our input alphabet was 0 and 1. But our full-blown stack alphabet had like capital Z's or maybe capital Y's or whatever. So here, the tape alphabet was all that, would be all that. It would be the zeros and ones and the Z's and the Y's and whatever else we had. And here I get to use an element of this thing that I write as a B with a slash through the stem. That's a blank. The blank has to be in our tape alphabet. So blank is an element of capital gamma. And we're going to be using those a lot. Those are like unused memory areas, variables that don't have any values. And we can go over to those squares that have blanks in them and write stuff on top of it so that we can remember. And that's, in fact, how we would implement a stack if we wanted to. We would go over to the blank and write something over that blank and say that we've pushed something onto the stack. Who's next? I'm going to skip little delta, put that down at the bottom. So I've got room for these other things. Q0. Q0 is the initial state. The starting state. See, we've seen all these before. That has to be an element of capital Q. So do Q accept and Q reject. Q accept. It's self-explanatory. It's the accepting state. If I had room, I would say also known as, to us, the final state. And Q reject is a rejecting state or a trap state. Q sub reject, rejecting state. There. That's 6 of the 7 pieces. The big one, we always save the big one for last, a little delta. Little delta is a transition mapping or a transition function. It was called transition mapping in the book where I got this, so I'm going to stick with that. Transition mapping. That takes an element of this set, capital Q cross capital gamma, and I'll go back and point at it and explain after I write it up here. From there to capital Q cross capital gamma cross a new state. This looks weird, not a new state, but a new set, capital L comma capital R. Here's the deal, and I'll make this more formal in just a second. We know these cross product of stuff of two sets is a set of ordered pairs. So it looks at a state, and the next tape symbol, which could be an input symbol. It could be a tape symbol that's not an input symbol, one of our stack symbols or whatever we're viewing it to be. But it looks at one state that it's in and one symbol where it currently is on the tape and decides what the next state's going to be. Surprise, surprise. And here's a new thing that I will write down later, but I want to get it out of my mind right now. This capital gamma here, an element of capital gamma, what it's going to do is whatever it saw in the square, the current square that was being scanned by the machine, it's going to replace that with a symbol. It could replace it with a capital letter, lowercase letter, an input symbol, a tape symbol, any valid tape symbol. And then one more thing, it's either going to move to the square to the left of where it was, or it's going to move to the square to the right. So all these pieces, we look at the current state, we look at the tape symbol, and then we go to a different state, a rewrite on top of the old one, that's new. We rewrite a new tape symbol on top of the old one, and then we move our read-write head, is what it's called, the read-write head of the machine to the left or to the right. You're dying for a picture, I just know you are. So now that I've managed to squeeze all that onto the board, I'm going to have to erase the whole thing so we can look at a fig and get a better intuitive lock on how these things operate. Actually, I guess it's more than just a fig. It's an example of what we might expect. Here is the initial tape. We assume that someone got to the machine before we did and put a bunch of stuff on the tape. What did they put on our tape? Well, we will assume that the tape is finite to the left. In other words, there is a first square. We could think of that as square 0, just like an array, and the square 1, square 2, square 3, and so forth. So there is an endpoint, so to speak, on the left, but not on the right. Weird thing. So if the initial input is A, B, C, D, E, I'm going to put another square and then the dots. If that's our initial input stream, just A, B, C, D, E, then we get to assume infinite blanks on the right. I keep saying infinite over and over, I know I do. But all that means is we don't have to worry about running out of squares where we might want to record stuff to simulate a stack or simulate a queue or simulate, a running total. We can actually construct Turing machines to do addition and multiplication and weird stuff like that. So we can assume infinite memory to record partial results over here on the right if we want to. So there's the initial tape, and let's say that our machine I'll do a before and after picture. Let's say machine M, our Turing machine M, is currently in state Q sub I. Imagine that. I just pulled that out of a hat. And let's see, it's pointing at, let's point at C. Why not? So the read-write head is currently examining C, and over here we've got A, B, C, D, E, blank, blank, blank. I don't know that I really needed to rewrite all of that, but that is a current configuration or a current state that the machine could be in. The after over here would be, it's still machine M, but it's gone to state QJ. Imagine that. So now we're in state QJ, and maybe we replaced C I still got A, B over here. We replaced C with F. Why not? Maybe F is a valid symbol in our tape alphabet. And then we'll still have D, and we'll still have E. Bunch of blanks. And the read-write head, let's say that moves to the right. So now it will point to the D rather than the C. How did I know all that? Well, in my mind, no, this is all a big lie, but I'm going to say it anyway. In my mind, I was imagining that we had a transition like this. It's just a specific example anyway. Forget the I and J. That's Q1, that's Q2, for crying out loud. There we go. Now, then there must have been in the table, if that's a valid transition for me to make, it must have said that if you're in Q1, remember we need an ordered pair over here that's a state And one of our tape alphabet symbols, C equals, where do we go? Oh no, it looks like we go to Q2. And it looks like we replace, I keep saying that, looks like we replace C with an F, and we move to the right. So I reverse engineered what that little delta transition must have looked like that allowed me to do that before and after picture. It says if you're in state Q1 and you're scanning a C, then you do this. You move to state Q2 as the state of your machine. You write an F replacing the C. So the C got wiped and replaced with an F, and then we move to the right one square, and now it's examining D as the initial state. Okay? While I'm at it, okay, board space down here. Configuration. Configuration is just a snapshot, an instantaneous view where you don't have to draw the picture and everything. So a configuration definition, this is not definition, it has a format. UQV, where little q is an element of capital Q, that's a state, and U and V are elements of, oops, it's not that, I'm sorry. Doesn't have to be input symbols. It could be any valid tape symbol, so it's capital gamma star. Good grief, that is so abstract. It's a configuration has this format, UQV, where all this is saying is we represent where Q is scanning on the tape by putting the things to the left of the read-write head in string U, and putting the stuff that includes the currently scanned symbol and anything to the right of it in V. That might not have helped at all whatsoever. But we can do before and after configuration over here to match these pictures. The configuration here, since the initial string was A, B, C, D, E, we had A, B, and then the machine was scanning symbol C, so I'm going to put Q1 right there. A, B, Q1, C, D, E. There you have it. And since I put the configuration in a box down there, I'll put it in a double box. New convention, instead of underlining everything, I'll just put boxes around it. That looks weird, but that corresponds to this picture. A and B to the left of the read-write head, and then my convention, my little touch to that, is to underline the symbol I'm scanning so I can just keep up with what the heck's going on here. So, in state Q1, scanning the C, then I would move to this other configuration. What is it now? A, B, F got left behind. We're in state Q2. And now we're scanning symbol D, so I underline that, and the E is still over there. So now, not only do we have before and after figures, we got before and after configurations. Did I do that correctly? Let me double check and see. I'm looking at D. D, I'm looking at you. And then the E is next to that, and the ABF are left behind on the left-hand side. Okay? And since today is fill up the entire board day, I'll mark off another box. Computation. I think we saw that in conjunction with earlier machines, but just so we got a complete set here, a computation is a valid sequence of configurations. A valid, meaning we got there by applying little delta over and over, a valid sequence of configurations. Now, why did I go ahead and put that up there? Well, these are intimately related. A configuration is like a snapshot. That's like one little frame of your movie, of your big roll of film, old school. One little snapshot of what's going on just right that instant. This is the whole movie. Computation, start at the very beginning, follow configuration, 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 all the way down to the end, and you got yourself a computation. What other terms do I need to explain? Well, you know what? I think I've already used up, yeah, I've gone past time. So I will pick up where I'm leaving off. We still haven't seen a real live Turing machine example, so I'm going to call this one done. I filled out the board a few times, and I'll see you online.